About organic chemistry. Oh dear. Sure, Graham. Organic chemistry. I kind of like the finer line. This is a whole new era for me here. Okay, so what do I mean when I say organic chemistry? What's an organic compound? Any ideas from the crowd? Good. Okay. Um, so yes, it's basically the chemistry of carbon compounds. So why the term organic, do you think? Why does that kind of come into play? Say that again? No. Think historically. Where do you believe early chemists would have noticed lots of carbon-containing compounds? Right, within living tissue, right? Within living things. Um, so living things, obviously, I think as you know from bio, contain lots of carbon compounds. So the name organic comes from the fact that early on, um, it was noticed that living things contain carbon-containing compounds. Now, organic chemistry has expanded much and way beyond just dealing with living things like it probably originally started out with. Um, what probably early chemists referred to as organic chemistry, we now call biochemistry, the actual chemistry of living things. And organic chemistry is strictly to do with carbon-containing compounds. So the next question might be, why do we have a special name? Why is there a branch of chemistry just dealing with these type of compounds? Why isn't there like, a branch of chemistry dealing with aluminum compounds, for instance? Why carbon-containing compounds? Anyone have any ideas? Yes. Okay, sure. Definitely the life aspect. It has to do with life, sure, so we're interested in it because we are naturally interested in living things. That's one reason, okay? But I mean, there's lots of other elements that are involved in life, right? There's water, or I guess it's not really an element, but there's oxygen, let's say, and hydrogen, and there's, lots of trace elements, even metals and so on. But they don't get their own branch of chemistry. So the life thing, although it's interesting, isn't really the reason why there's a whole branch of chemistry uh, dedicated to this. Any other ideas? Where's carbon on the periodic table? Well, it's the I guess it's the 14th group or group 4. What does that tell you about its valence? 4. Okay, so it's right in the middle between metals and nonmetals, generally considered obviously a nonmetal, or I guess maybe more a metalloid. And it has 4 valence electrons. In other words, its combining power is 4. Um, how many other elements on the periodic table do you see that have a combining power of 4? Are there lots? Really, the only other one is going to be silicone, right? Um, there's lots of silicone around. I mean, the sand on beaches tends to be mainly silicone. Um, and so really, carbon is kind of special. Silicone, I don't believe, is capable of forming the same, wide variety of basic building blocks that carbon is. And so carbon is essentially kind of a special element in that respect, the fact that it has 4 bonds. Okay, what can carbon do with those 4 bonds? It can bond, and specifically, an important thing that it can do is it can bond with itself. And someone mentioned earlier that that makes chains, and these chains are very important. Lots of life's building blocks rely on carbon chains. Lots of things to do with living things have to do with carbon chains. But bonding with itself, it allows lots of important features about carbon, right? So it allows chains, right? Allows double bonding, which turns out is sort of important, and even triple bonding. Okay. So that has, repercussions for life, and it also has repercussions for non-living organic chemistry, such as the creation of things like polymers, so plastics and so on, rely on this ability of carbon to form chains and to form chains with itself. And it also, not only can it bond with itself, it can bond with essentially, most other elements on the periodic table. So what this essentially leads to is this wide variety of potential molecules, carbon-containing molecules that are out there. So many, right, that it's probably in the millions, if not even higher, of molecules that contain carbon. All right. Just think about your bio classes and think about all the different chemicals you run across, from sucrose and starch and so on to DNA, right? There's carbon right through the whole system. Okay, if you look around the room right now, anything that's made of plastic has carbon chains inside of it, glues and so on. And even like the fringes of physics and chemistry, things like graphene and nanotechnology, a lot of that contains carbon as well. So that's why it kind of has its own area of chemistry. It's a very pervasive chemical that makes up a lot of our world, and we've harnessed its power to, I guess, make our lives better, right? What's I going to say here? Why did I put a number 5? Anybody know? Okay. Right. Okay, right. Yes. Okay, so this has so yeah, so I've sort of been talking mainly about the life aspect. So um implications right through chemistry and physics. All right, so one place to start with this is looking at what is called the homologous series. What does the word homologous mean? Same, similar, right? Not the same, but similar, okay? So like, things that are like. So let's start with the simplest carbon compound we can think of. Maybe not the simplest, but the simplest that would be in a homologous series, and that's methane. Okay, so methane looks like this. CH4. Okay. A homologous series has similar compounds, the same but similar. And so if we add another carbon to it and we saturate it with hydrogens, we get C2H6, which is called ethane. Don't worry about the naming right now. I just want to show you what a homologous series looks like first. And I think you can probably see where this is going. Often it's a convention in organic chemistry because it would get tedious really, really fast to write hydrogens in. Sometimes if you want to show the skeleton, you would just leave the H's off. So oftentimes you'll see organic compounds just written like that. The assumption being that unless they're showing you specifically that there's something other than hydrogen on there, you just assume there's hydrogen on there. Okay, so you might see this written like this. So C3H8, okay, etc. Looking at this, and without drawing another picture, What do you think the next molecule in this homologous series, what do you think its formula is going to be like? C4H10. Okay. Then what? C5H12. Then what? Good. Do you think there's like some sort of formula we could write that tells you about everything in this homologous series? Is there a way we could write this down? Like, let's say we say C N H 2N plus 2. Does that work for everything? N, let's say N's 5. 2 times 5 is 10 plus 2, 12. 6. 12 plus 2 is 14. Perfect. Okay. This is the formula for the homologous series called the alkanes. Okay? Humor me. This is the alkane formula. Okay? Homologous series exist all the way through chemistry. There's, there's ones where, there's one double bond. There's ones where there's, say, like functional groups, like alcohol groups and so on, amine groups. And this is the general way that they're looked at, okay? They would all have sort of a formula of this kind of nature that talks about them. So this homologous series that we just drew is called the alkanes. Okay. Before we get too far into this, let's talk about the ways that we can represent formulas or represent these, carbon compounds that we're talking about. So we see a couple here, right? We see one that's I guess the full structural or skeleton drawing, which can be done in one of two different ways. Okay, so this is where we're drawing out the whole entire, molecule, bond by bond. So let's, just before we go on here, let's do ways of writing these down. So ways representing organic compounds. And let's take octane. We'll get into naming, how we name these things in a minute. But octane, that's going to refer to 8. So C8, 16, 17, 18, right? H18. It should be octane. Okay. So let's think of ways to write this down, because there's a lot of different ways. What do you call this way of writing it down? What's that called? This is the common way that we write down molecules. What would you say that's called? Good. That's just your standard molecular formula. The thing about it is, in organic chemistry, if we start to look up here, you can't really see it here, but if you have a chain that's 8 long, with just that molecule, does it make a T shape? Maybe there's some branches coming off of it, and so on. And we'll look at that in a bit. So the molecular formula is a little bit limited. It doesn't give you a lot of insight into how these atoms are all arranged inside the molecule. Okay, so there's that. That's one way. Now there's also another way that would look something like this. Wait, is that right? No, it's not. Sorry. Step back. There. That's better. Okay, what do you call that type of a formula? Good. This is the empirical formula. What is the empirical formula again? How do I describe what the empirical formula is for a compound? Alex. Right, exactly. So yeah, like the lowest common, I guess, multiple, is that what it would be? Lowest ratio, that's right, that's a better word. So it's the lowest ratio of elements. That's right, it's the lowest ratio of elements. That's a good way to put it. Okay? Now the empirical formula, you might say, like, what a useless thing. However, there's lots of chemical processes that you can use to find out what the ratios of different elements are in a substance. Okay, so usually it's not like you're going to say if you knew this, you'd ever go back and use the empirical formula. However, if you're doing analytical testing, your testing methods might get you to here, all right, and then you might need other methods to figure out what the actual atom looks like, or sorry, what the actual molecule looks like. We have done some stoic where you have to figure out what the molecular compound is based on the empirical. So hopefully you kind of can remember that. Empirical isn't really, as far as I know anyway, useful if you're working backwards. If you already know this, I don't know why you would go back to this, but this might be all you can get from your testing. Okay? So there's two ways. There's also a condensed structural. I'm going to draw that after I draw the actual skeleton of this thing. So the skeleton should have 8 carbons. Okay, these of course, as they normally do, represent single bonds. Not really a lot of sense in writing out all of those H's. This is the skeleton formula, okay, with or without H's. Okay? It's possible that they include all the H's. Oftentimes chemists leave that off. There's even a more bare bones or basic skeleton formula, and I'll show you what that looks like. Now these carbons, and we'll make models of this, but the way that they line up is not in a perfectly straight line like this. They'll actually like zigzag. So 1, 2, 3, 4, 5, 6, 7, 8. This also represents the same thing, okay? I don't know what the name of this type of formula is. I always call it like simplified skeleton maybe. We can make up our own word for it, simplified skeleton. Now what is this saying? What it's saying is these represent the bonds between carbons without actually drawing the carbons themselves. So you assume there's a carbon there, there, adding up to 1, 2, 3, 4, 5, 6, 7, 8 carbons, and no lines or dots for H's. They're just assumed to be there. So this is another way to represent octane, okay, that you might run across. I don't know how common this is, but you do see this from time to time. Are you still with me? Perfect. And then the last one is the condensed structural formula. So if we think about it, octane looks like this. It's got a CH3 on one end, right? And it's got 1, 2, 3, 4, 5, 6 CH2s in a row. And then it's got a CH3. Okay? So this is yet another way to write octane. This is known as the condensed structural. Now this gives a lot more information, right, than does just the simple C8H18, okay? It tells you that these are all lined up in a row, and that there's 6 of them, okay? So in other words, there's no like strange branches off of here or weird stuff going on. It's all just in a line of CH2s all the way down, okay? So that's quite a few different ways of representing the same molecule, right? And there's a few more that aren't paper-based. Like for instance, you can actually model these with molecular model kits, which we'll look at. And there's actually one other one. It's called the stereo representation. For C8H18, probably a stereo isn't going to be useful. However, it might be useful for something like methane. Okay, and I'm just gonna do methane in this way. And what it's basically showing you is it's a way, and I think we probably saw this before, a way of representing on paper where these are in space. Okay, so see at the center, if I draw just standard lines, it means that those are on the plane of the paper. Okay, so two of these hydrogens are in the same plane, and then one will go back. To represent back, we draw dots, and one will come forward. To represent forward, we draw this, like, I don't know, perspective. Okay, so what this is trying to show is that you have this molecule that projects H's off of it. Now, why do the H's orient themselves in this way? Think back. What makes them end up at these points in space? Is that what it is? We studied this. Remember this? What does that mean? Good. Valence shell electron pair repulsion. So what we're saying is, right, these represent areas of negative charge, and areas of negative charge repel one another. So these are going to organize themselves such that they're as far away from each other as possible. Okay? Do you remember what the bond angle would be on something like this? That ring a bell? I hope so. I hope so. You guys have started studying, I'm sure. Okay? So VSEPR, we've taken that a while ago, but this representation here, this stereo-optical representation, is important in organic chem, especially when we start to change these to other things that are not H's, like chlorines, for instance, or whatever, or different functional groups. It's sometimes very important as to where they are. Okay? So far, so good. Let's get on to naming. Actually, before we do naming, let's talk a little bit about the properties of homologous series. So properties of homologous series. Let's start with alkanes, okay? What do you suspect happens in terms of the physical properties as you get larger and larger and larger alkanes? Physical properties of that simple series that we talked about, right? So C, H4, C2, H6, etc., etc. Okay, as we go up the larger and larger and we get greater and greater and longer chains, things going to happen to the physical properties. Okay. So when I say physical properties, then what do I actually mean? What are some physical properties of these things? Yeah, exactly. So melting point, boiling point, density, say. Anything else? We'll go etc. Okay? What do you think happens to the melting and boiling points as we climb up a homologous series? What do you suspect and why? Good. Good. So it was said that the melting point and boiling point will increase. This is true. And they will increase because as these molecules get larger, the van der Waals bonds, for the intermolecular forces, grow. Okay, the larger the molecule, the more, the influence of all of those electrons that are hanging around in these molecules have on the molecule next door to them. Okay, so what you'll find is you get sort of this relationship. This is general. I'm not going to actually put real boiling points in, but what you'll find as the carbon number increases, both the melting point and the boiling point tend to rise, okay? And they rise kind of in this fashion. Can anyone think why there's not a linear rise in melting point and boiling point? Why is this not linear? Think about the difference between this to this versus say this Let's think about molecular weight of this. What's the molecular weight of this? 16. How about this? 30. Good. So it's essentially, basically, pretty close to a 100% increase, right? Can you do the molecular weight here? Use your calculator if you have to. 214. And how about here? What's the percentage increase from 114 to 128? Less than 10%? Right? So less than 10%. Oops, that's the wrong way. 10% over here. Okay. So yeah, so that's kind of the reason, right? As we're adding carbons higher up the chain, there's less overall change in the molecular size. So you get a much larger increase at the beginning, and then that sort of tails off. This is true for all homologous series. They all follow the same general rule. It never goes in reverse. Does it? Excellent. So one more thing to talk about is solubility. So in general, organic compounds are not soluble in water, tend not to be soluble. Why would that be? Why would they tend not to be soluble? Especially the alkanes. The alkanes are definitely not soluble. Right. Especially the alkanes are non-polar, not especially, but the alkanes and other things like alkanes. However, there are soluble organic compounds. Okay, so ones that are soluble have these general properties. They're small, and they're polar, or have polar groups on them. Okay, or the other thing that can make them soluble is if they become ionized. So the acetate ion, for instance, is soluble. So acetic acid is soluble, for instance. But long chain carbon atoms tend not to be soluble. So what will happen with like, let's say we have a simple alcohol. So something that's an alcohol will have this group on it somewhere, right? An alcohol group. So let's talk about some simple alcohols just quickly. So you might have this. So we've got methane, but we've replaced one of the hydrogens with an alcohol group. Okay, that gets the name methanol. If we put 2 carbons on here, like with methane and ethane, you get ethanol. Okay, and so on, propanol, etc. Okay, well, it turns out that ethanol and methanol are both highly soluble in water, but as you get higher up the chain, you get less and less solubility until finally, I believe around, I can't remember exactly, but I'm thinking about maybe the 4 or 5 carbon alcohols stop being soluble. Can you explain why that would be? Yeah, I think, yeah, That's probably a good way to say it. Basically what happens, right, is this oxygen is highly polar, okay? And you end up with sort of a negative polarity on this whole molecule. Because it's a small molecule, water can now surround this and pull it into solution. Same goes here. But once you start getting to here, yeah, this is still negative, but there's a long enough, and as you continue it, right, as you add carbons, there's a long enough non-polar section that water can't surround this and pull it in. So when you see things like, a classic example might be like your salad dressing. Okay? You can shake it up, and you can get a colloidal suspension where the little droplets of the oil are suspended through the liquid part. But if you leave it sit for a while, those oils start to separate out. Okay? So yeah, so organic compounds tend not to be soluble in water. All right, that's enough. We'll go over naming tomorrow, or next class, I should say. That was a half-hour lecture, so that's probably long enough.